Now we go down to the memory. Let's see a node in memory, where it sits, how many bytes it takes, and why the order lives in the pointers. Nodes can sit anywhere in memory. Let's give them real addresses and see what holds the list together. Here is the first node. Node 10 sits at address 1000. Its next field holds 3000, which is node 20's address. Follow that link to node 20 at address 3000. Its next field holds 2000, which is node 30's address. And here is node 30 at address 2000. Its next field holds null. So each next field stores the address of the next node. On purpose, the three nodes sit out of order in memory. The addresses are scattered, but the order 10, then 20, then 30 comes entirely from the next pointers. And remember, teaching addresses like 1000 are just for the picture. Real malloc gives you unpredictable, non-consecutive addresses. This is our first structure built on real pointers, so let's define one bridge now. The tail's next field holds nothing, and nothing has two names in this course. On the left is the pseudocode, list traverse of head. We set cur to head. While cur is not null, we visit cur.data, then we set cur to cur.next. In pseudocode, we write this end marker as NIL, which just means no node. On the right is the same loop in CA for loop. We start with node star cur set to head. We keep going while cur is not null. Each round we do cur becomes cur arrow next. Inside, we visit cur arrow data. In C, the end marker is spelled null. This is the rule locked for all 21 chapters. Pseudocode NIL is exactly C null. A next field holding null is a link to nothing. That is the end of the list. Later, a search that returns an index will use -1 for not found. That is a separate sentinel, not null. Let's zoom into one node byte by byte. On the 64-bit setup we assume here, one node takes 16 bytes. The exact size and padding are set by the platform, so they can differ elsewhere. This is the node holding 10, at base address 3000. This is the key memory map for the whole chapter. The whole block sits on the heap. This band marks it. It is one node struct, laid out from low addresses at the bottom to high addresses at the top. At the base, 3000 is the data field. It holds the value 10. The int takes 4 bytes. Next, at 3004 come 4 bytes of padding. They are empty. We need them so the pointer that follows starts on an 8-byte boundary. That is called alignment. An array cell had no padding, but this node does. On top, at 3008, is the next field. It holds 7000, the address of the next node. The pointer takes 8 bytes. So 4 for the int, 4 of padding, and 8 for the pointer gives 16 in total. One thing to keep straight. The next field is not the successor node itself. It stores the address of the successor. The pointer is the extra cost we pay to stop storing nodes next to each other. So the three nodes sit scattered in memory, but the list still reads 10, then 20, then 30. Let's see why. The next pointers alone set that order. Look at the addresses. In address order, 7000 is highest, then 4000, then 3000. But the list order is still 10, then 20, then 30. Node 10's next name's node 20. Node 20's next name's node 30. These next links are what make a structure linked. Now the full picture. Here, head is a local variable, so it lives on the stack. The malloc nodes live on the heap. If head were global or static instead, it would live somewhere else, so this is the common case, not an absolute rule. Up here on its own is head. It is a single pointer and it sits apart from the nodes on the stack. Its only job is to hold the location of the first node. Here it holds 1000. The arrow from head reaches down into the heap to the first node. Node 10 holds the value 10 and it sits at address 1000. So head on the stack reaches across into the heap. Lose head and you leak the whole chain. Node 10's next points to node 20, the second node on the heap, at address 3000. Node 20's next points to node 30 at address 2000. And node 30's next is null, the end of the list. Let's do a quick learning check. Suppose a bug sets node 20's next field at address 7008 to null. What does traversal from head print, and what happens to node 30? Pause and think about it before we reveal the answer. Here is the answer. Traversal prints 10 and 20 then stops. The early null reads like the tail, so the walk ends there. Node 30 stays allocated, but now nothing points to it. It is unreachable. That is a memory leak. These few expressions are the #1 source of linked list bugs. Let's keep them straight. In this example, head is stored at stack address 2000 and head holds 3000. First, head on its own. This is the pointer variable's value. Here it is 3000, the address of node 10. Second, star head. The star means dereference. It gives you the node it points at. Here that is the struct holding 10 and 7000. Third, head arrow data. This reaches into that node and takes the data field. Here it is 10. Fourth, head arrow next. This takes that node's next field. Here it is 7000, the address of the following node. Fifth, ampersand head. The ampersand means the address of. This is the address of the head variable itself. Here it is 2000. That is a different address from everything else. Two things to remember. Head arrow next is just shorthand for star head in brackets dot next. You dereference, then take the field. An ampersand head is a completely different address. It names the box that holds the pointer. We will need it later to change the caller's head.